Welcome to exercise 11.3, where we take a look at multi-step experiments and how we can represent them using tree diagrams. So previously in 11.2, most of the experiments and trials that we saw were just one-time trials. Now, when we display multi-trial experiments, the best way to do it is probably via a tree diagram. So down below here, we've got a nice little example of two experiments, a coin toss and then a marble pick. And we can see here you've got a 1 in 2 chance of drawing a heads or a tails from the coin toss. Sorry, or flipping a coin. And then from the marble pick, you've got a 3 in 4 chance of drawing a red marble, a 1 in 4 chance of drawing a blue marble. And clearly there's only 4 marbles in total in the bag, and 3 of them are red. 1 of them is blue. And then we can write out our sample space, which we call the outcome, to the right of our tree diagram. And then further to the right of that, we have ourselves the probability, which we multiply the branches with. So each line with a fraction is what we call a branch. And then we have the experiments labeled at the top. Let's see what it looks like as an example. So just this last part here, basically all the outcomes added together will give you an outcome of 100% or 1. Alrighty, example 1. So what we have here is a weird 3-sided die, and a name is picked out of a hat that contains 3 girl names and 7 boy names. So how do we start this tree diagram? Well, we have a 3-sided die. So we say die. Maybe let's just write dice since there's only one. All right, since die implies it's plural. Okay, and then we have names. All right, we have outcomes. Then lastly, we can write potentially the odds. So 3-sided die. Let's start the branches here. So we could have a 1, we could roll a 2, or we could roll a 3. Now each one of these is 1 out of 3. 1 out of 3. Then we get to the name. So you've got girl and boy as the 2 possible outcomes. So let's say this one is girl, this one here is boy. There's 10 names in total, 3 of them are girls. 7 of them are boy names. We do the same here again, girl, boy, so 3 are girls, 7 out of 10 are boy names. And we have girl and boy, so 7 out of 10. And then for girls, we have 3 out of 10 again. All right, so here we have the outcomes. So we could get a 1 and a girl. Here we can have a 1 and a boy. So here we roll a 2 and then get a girl's name. Here we get a 2 and roll pick out a boy's name. Then we have a 3 and we have a girl's name. And then we have rolled a 3 and pick out a boy's name. Now, why do we do this? I don't know. I don't think this is very practical in real life, but it's just an example to show the likelihood of the outcomes. So the odds here would be 1 on 3 times 3 on 10. For 1 and boy would be 1 on 3 times 7 on 10. For 2, well, they're all going to be 1 on 3, aren't they? This one is going to be 3 on 10, 1 on 3. Let's just write 1 on 3 for all of them, because that's a probability of rolling a 1, 2, or 3 on the 3-sided dice. getting a boy, that's 7 out of 10. Girl name, 3 out of 10. And lastly here, 7 out of 10. All right, you put that into your calculator and you can get yourself your answer. So, tree diagram, all done. Question B, calculate the probability of rolling a 3, then choosing a boy's name. So rolling a 3, choosing a boy's name. So the branches that we go down is this one. So we see the odds are going to be 1 on 3 times 7 on 10, which is going to be 7 on 30. Okay. 7 on 30, can we simplify that? Not really. What's that? That's like that's 0.23 recurring, which is 23.33%. Look, any of these answers are acceptable. They all mean the same. Okay. Choosing a boy's name after rolling an odd number. Alrighty. So let's do this one in green. So choosing a boy's name after rolling an odd number. Okay, so it'll be this one because 1 is odd. We've got boys. It'll be this one as well. Okay, because 3 is also odd and we get a boy's name. So what we have is the situation where we have to add 2 branches. So the first branch, we have 1 on 3 times 7 on 10, plus the last branch, which was highlighted in yellow, which is 1 on 3 times 7 on 10, which means we are going to get ourselves an answer of what's this? 7 on 30 plus 7 on 30, which means we get 14 on 30. What is that? 14 divided by 30 is 0.46 recurring, which means it's about a 46.67% chance. All right. So yeah, when you got multiple branches, you want to add the odds together. Okay, so we'll put those color coordinations like so. Alrighty, let's take a look at 3 steps. So this time we have a, let's see if we have enough room. Let's try and create more room. Let's see, a coin is biased, so the chance of it falling on heads when flipped is 0.75. Okay, so if we go back up, what do we call it? That's how I labeled it, so let's call it coin. So maybe let's call it like toss 1. Toss 2. Toss 3, outcome, and then odds. All right. Let's branch it out nice and far because there's going to be, actually that's, when we draw a tree diagram, we always want to make sure our center dot's actually pretty low, because you'll see why. When we write heads, when we got tails, okay, this one is 0.75. So that means getting a tails is 0.25 because the coin is weighted to the heads. So it's more likely to get a head than a tail, unlike a conventional coin. Then in toss 2, if we get a heads, we can also get a heads and a tail. We can also get a heads and a tail. Toss 3, we can get a heads, a tail. This is why we need a space. A tail, a head, a tail, and heads, tail. And then we write the odds in. So 0.75 or 75% chance for heads. Let's find all the head options. Super tedious. And the idea is eventually you'll get so good at it that you won't need to draw a tree diagram to solve these sort of problems. All right, tree diagrams drawn. Every time we get a heads, we have a 25% chance. Every time we get a tail, we get a 25% chance. Every time we get a heads, that's a 75% chance. So the first outcome here is 3 heads, head, head, head. Second one is head, head, and a tail. Third one here is so head, tail, head. Head, tail, head. Then we got head, tail, tail. Then we have the tails first now. So tail, head, head, tail, head, tail, 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 head, and then triple tails. So the odds are going to be 0.75 times 0.75 times 0.75. So you can say that's 0.75 cubed. Then we have 0.75 squared, because there's 2 heads now. So previously there were 3 heads. That's why it's powered to 3. I mean, if you want to write 0.75 times 0.75 times 0.75, you can, but I'm just abbreviating it. For tails here, this is then going to be 0.25. Everything's multiplication. Here we have 0.75 squared again. Actually, we don't need brackets. Why do I have brackets here? No need for these brackets. Okay, why do we have 0.75 squared? Because we have 2 heads and a tail. Doesn't matter which order. It's always going to be the same sort of odds because it's the same outcome. You get 2 heads and a tail. Here we have 1 head, so we get 0.75 times 0.25 now squared because there's 2 sets of heads. For those who like to write it spaced out, that's fine. I've just run out of room here, so I've got to use powers. Here we've got 0.25 for tails and then 0.75 squared because we get 2 heads. This one here is 0.25 squared times 0.75. You got 0.25 squared times 0.75. And then this last one here is 0.25 cubed. All right, so hopefully that's not too messy. And we can sort of follow each of the branches that lead to the outcome. So calculate the probability of head, tail, tail. Now, this is kind of vague. Let me think. Does the order matter? I don't think so. So the order actually does matter. Why? Because the other questions you can see here ask for just probability of 1 head and 2 tails. Now, if it says head, tail, tail, we want it in head first, then we get 2 tails after. All right, so let's investigate which branch this will be. So we get a head first, and then tail and tail, which is this one here. Right. So this is 0.75 times 0.25 squared. Let's see what we get. 0.75 times 0.25 squared. 0.046875. What's that? That's like 4. Let's just round it to 4.7%. Okay, so you got about a 4.7% of drawing this line. Now, why does it look so low? It's because tails are rare because the coin is loaded, meaning it's not a fair toss. Okay. Probability of drawing one head and two tails. Actually, let's use yellow. Probability of one head and two tails. So let's go back to our tree diagram. Which one has one head and two tails? Well, this one here has one head and two tails. This one here has one head and two tails. This one here has one head and two tails. And that's it. So we take those odds. So we have 0.75 times 0.25 squared. We want to add that with 0.25 squared times 0.75. And then the third one, 0.25 squared times 0.75. What you notice is all the odds are the same. And hopefully we have enough space. Yes, we do. And we can go and add them together. All right. So input everything into your calculator. So 0.75 times 0.25 squared plus 0.25 squared times 0.75 plus 0.25 squared times 0.75. This will give us an answer of 0.140625, which is 14.06%. Okay, and doesn't tell us what to round to. 1 or 2 decimal places will do. All right, last one. Probability of at least two tails. So 2 tails or more is what we want to see in the outcome. So 2 tails or more. This one has 3 tails. This one has 2 tails. This one has 2 tails. Not this one because it has 2 heads. This one has 2 tails. And the rest of them are all mainly heads. All right, so we add up all the blue outcomes. So there's 4 of them. You have 0.75 times 0.25 squared. Then you have 0.25 squared times 0.75. Then you got 0.25 squared times 0.75. And then lastly, you've got 0.25 cubed. Input everything into your calculator and you should get yourself your answer. So 0.75 times 0.25 squared plus 0.25 squared times 0.75 plus 0.25 squared times 0.75 plus 0.25 cubed. Hopefully I've entered all that correctly into the calculator and we get ourselves an answer of 0.15625, which is like 15.63% roughly as our answer. That's all for exercise 11.3. Let me know how you go and if you have any questions. Thanks, everybody.